Hello and welcome back to the channel. Today we are going to discuss about rank of a matrix. So the rank of a matrix is a fundamental concept in linear algebra that plays a crucial role in machine learning, data science and artificial intelligence. It helps in understanding the dimensionality of data, identifying dependencies between variables and optimizing models. Now, what is actually rank of a matrix? So the rank of a matrix is the number of linearly independent rows or columns in the matrix. So it tells us how much useful information that matrix contains. The higher the rank means the matrix has more independent data. A lower rank means the matrix has redundant or dependent data. Now in mathematical terms, when we look at its definition, it goes like for an m cross n matrix A, the rank of A is the number of linearly independent columns or rows it has. So the key properties involves firstly, column rank equals to row rank. That is the fundamental theorem of linear algebra. Next property is rank of A is less than equal to min mn, meaning the rank cannot be larger than the smaller matrix dimension. Lastly, the third property is if A is a square matrix that is n cross n and has full rank n, then A is invertible, that is, it is not singular. Now let's look at some examples. Firstly is a full rank matrix. Suppose we have a matrix A with elements 1, 2, 3 and 4. The two columns are linearly independent, that is, one is not a scalar multiple of the other. So the rank of A here will be 2. Next example is rank deficient matrix. Now consider a matrix B with 1, 2, 2 and 4 as its elements. Here the second column is twice of the first column. That is, they are not independent. So the rank is only 1. So rank of B is equal to 1. Now we know what rank is. Now how we can find it? We can find it using row echelon form or reduced row echelon form. So the steps to follow to find rank of a matrix are firstly, convert the matrix into the row echelon form or the upper triangle form using row operations. And then count the number of non-zero rows. This will give you the rank of that matrix. Now suppose we have a matrix A. It is a square matrix of size 3 cross 3. We will perform row operations and form upper triangular using these row operations. So the first operation that we will perform is subtract 4 times the first row from the second row. After this operation, we will get this as our final matrix. The next operation we would perform on this is subtract 7 times the first row from the third row. After this, here we get 2 zeros. The next operation is dividing row 2 by minus 3. This will be our final matrix after that. The last operation that we will be performing is add 6 times of second row to the third row to make the second column's lower entries as 0. So this will become our final output. So what will be the rank of A now? There are 2 rows that are non-zero. So the rank will be 2. Now let us talk about rank and linear dependence. So if the rank of a n cross n matrix is less than n, its rows or columns are linearly dependent. If rank of a matrix is equal to n, the matrix is full rank and has independent columns. Rank helps in feature selection in machine learning, that is, highly correlated features lead to rank deficiency. The next topic to discuss is rank and determinant and how they are related to each other. So for a square matrix A that obviously has a size of n cross n, if rank is equal to n, then determinant of this matrix will not be equal to 0, hence the matrix will be invertible. And if it is less than n, then the determinant will be equal to 0 and the matrix is singular, that is non-invertible. So this property is used basically solving linear systems and check multi-collinearity in regression analysis. Lastly, applications of matrix rank in data science, ML and AI we will talk about. Firstly, in dimensionality reduction, either we are working with PCA, that is principal component analysis, or SVD or singular value decomposition. The rank of the covariance matrix determines the number of principal components in them. Then is feature selection in machine learning. So a dataset with correlated features has a lower rank, meaning some features can be removed without losing the information. So redundant features reduce the efficiency of models, and then rank helps identifying them. Then the third application is in linear regression. If the design matrix in linear regression has full rank, then the model has a unique solution. Else, if the matrix has a low rank, we have multi-collinearity leading to unstable predictions. Lastly, in neural networks, so in deep learning, low rank matrices are used to compress the models and reduce computation costs. And then rank helps in understanding activation functions and weight matrices in deep networks. So, the rank of a matrix is a critical concept in linear algebra, or you work with machine learning and AI. It helps in determining data independence, identify redundant features, optimize regression models and neural networks, reduce dimensionality using PCA and SVD. So that's all for this video. And if you have any questions, then drop down in the comments. I will be happy to help you all in them. And in the next video, we will move on to orthogonal projections in foundational mathematics. See you in the next one. Till then, happy learning.